AQUABIZ, all the best knowledge for aquatic system.
So this presentation is a little bit of a variation on a presentation that I gave when I was here in September. So for those of you who were here, you'll recognize some of these slides perhaps. And I was asked by the USSEC regional manager to basically take some elements from that presentation and focus it in on this idea of bioremediation. So, and the context, you know, I want to put it in the context of Asian shrimp ponds, both soil-based and with liners, but really there is still a lot of soil-based farms, and so that will be the effort. So here's an overview. I want to talk about system waste loading, and then a little bit about sediment chemistry, because I think there's a lot of misunderstandings about that, with a focus on organic matter dynamics, and I mentioned that in the previous presentation. And then I want to get into, you know, the actual tool of bioremediation. How do you improve conditions in the sediment, particularly with respect to organic matter? And then a little bit about improving conditions in the water column. And then I also want to, at the end, talk a little bit about hydrogen sulfide, which can be a serious problem in both lined ponds and unlined ponds. So let's start with this graphic that was produced by Dr. Claude Boyd. And you know, I want to make a point here that you know, if you start with feed and you end up with harvested shrimp, and you consider the amount of nutrients that are in the feed, okay? So let's just say 100% of the nutrients that are added to a pond are in the feed: carbon, nitrogen, phosphorus. And so what percent of those nutrients do you think we're actually harvesting? And it turns out it's something like 25 or 30% is what you're actually harvesting. So that means that 75% of the nutrients that you're added to the pond is actually released to the water column, okay? And in fact, for every kilogram of feed that you're adding to the pond, you're growing 3 kilograms of algae, okay, of phytoplankton. So you're adding a lot of organic matter to the pond, you're fertilizing that pond, and most of the nutrients that you're adding in the feed ends up in the water, okay? And so as farmers have to deal with the consequences of that efficiency. That's just an inherent efficiency of it. So if we look at this on a little bit more detail, we can actually calculate how much nutrients is going into a pond, and it's pretty straightforward. So up here, this would be a calculation of a feed that has about 32% protein, and this is a typical composition of shrimp that are harvested. And we can use these formulas here to determine the waste loading of nitrogen and phosphorus into the pond as a function of the feed conversion, okay? So it's feed conversion times the nitrogen in the feed minus the nitrogen in the shrimp, and that'll give us the kilograms per ton. So I've gone through that calculation, assuming a feed conversion of 1.5, and you can put your own number in there if you want. So again, if we assume 100% of the nitrogen is in the feed, 36% is harvested in the shrimp, and 64% is released to the pond. And again, you could do the same calculation with phosphorus, and 82% of the phosphorus is released to the ponds. And you know, most of this phosphorus is in solid form, okay? And most of this nitrogen is in dissolved form, okay? But that's neither here nor there. The point is that most of it is released. Most of the nutrients that are in the feed are released to the pond, and that's just an inherent efficiency. So this is an example of a chemical budget for a shrimp pond. There are a lot of these out there in the scientific literature. I just picked this one as an example, and I believe this is for an intensive pond context, so it's relevant to the situation in Thailand. Most of the nutrients that are added to the system are in the feed. And what I wanted to point out was that there's a certain fraction of the carbon, nitrogen, and phosphorus that actually accumulates in the sediment during the production cycle. That's just a natural process. Now again, if you have a system where you're removing solids, a lot of this material will be removed from the pond as well. But I just wanted to give you an idea of the general the general picture with respect to nutrient flows in a production pond. So I had this graphic in the previous presentation, and I brought it in here because I think it's important. And I want to emphasize this point about feed oxygen demand, and particularly with respect to the organic matter that you're adding, that basically half of the feed oxygen demand is associated with the decomposition of organic matter. So if you get that organic matter out, you spare oxygen that you're adding with aeration, and you can use it to grow the shrimp crop instead. Okay, so let's talk a little bit about the sediment now. So if we go outside in the garden here, and we take a soil sample, and we look inside that soil, basically half of the soil is the mineral particles, okay? The actual heavy mineral particles that you feel. And about a quarter of it is water, maybe a little bit more because it rained last night. And about a quarter of it is air, all right? And that's really important. So you have these particles, and here's air in there. And that air is really important because that provides the oxygen that the bacteria need that are in the soil to be able to work. Now, in a shrimp pond, the sediment doesn't have any air. So you basically have 50% air and 50% water, all right? And that has profound effects on the chemistry of the sediment, of the soil that's flooded, that's completely covered with water, that's in a shrimp pond. And I want to talk a little bit about that now. So one of the things that we can do is we can make a profile. If we take a core of the sediment, this is basically what we see. If you come down to the pond bottom, you see very close to the pond bottom, kind of like a biofloc. You have this accumulation of organic matter. And then you have this very thin oxidized aerobic layer. So this is the layer of the sediment that has oxygen in it. And then below that, all of this sediment is anaerobic, okay? It doesn't have any oxygen in it at all. So, you have these profiles. So this is what the sediment looks like. And here is that very thin oxidized sediment layer. Typically it has that nice brown color. And then below it, you'll see this black soil, okay? So look at this pond over here. So this means that pond, when they drained the water, it did not have any brown layer at all. And that has some serious consequences for water quality as well. This is what you want to see. This is what it should look like all the time on the pond bottom, because that little skin of oxidized sediment serves as a barrier to the diffusion of reduced substances, chemically reduced substances that are in the sediment, and it keeps them from diffusing into the overlying water. So that's a desirable condition. So if we look at this, if we measure the oxygen concentration as we come down into the sediment, and we can see that very, very quickly, and look at the scale here, this is millimeters. So within 1 or 2 millimeters, there's no oxygen anymore in the sediment. It's gone. And so we can't really use an oxygen meter anymore to measure the sediment conditions. Normally we use, in this case, a platinum electrode that measures oxidation reduction potential, all right? And you can see that it becomes more and more negative as you go down into the sediment. So the way to conceive of the sediment is that it has layers. It's like layers of the cake. There was some cake just out here. And so we have layers of the cake. And in each layer, there's a different set of chemical reactions that are going on, all right? And we don't have time to get into that today, but just think about the sediment as a layered sediment. and that the surface, just that very, very thin crust or skin, has oxygen, and it's important to maintain that layer. Okay, so what this graphic shows is that if you look at the chemistry of the water that's inside the sediment, that's down there in the sediment, it tends to have, this is time over here, April, May, June, July, August. So here's ammonia concentration. The water, the pore water that's in the sediment tends to have a high concentration of ammonia. It has a high concentration of dissolved phosphate, and it has a high concentration of dissolved iron or soluble iron. All those are a consequence of chemical reactions that are occurring in anaerobic conditions in the sediment. You don't want this stuff to come out of the sediment. You want to keep it there. And the way you keep it there is to maintain that thin barrier of oxidized sediment surface. Okay? All right, let's take a look at organic matter now. And this is an interesting graphic because what this shows is a profile. So we're cutting through the sediment of ponds of 3 different ages. So we have ponds that are 2 years old, 23-year-old, and 52 years old. So these happen to be freshwater ponds, but the dynamics are going to be the same. But what you see, a couple things I want to point out. One is that regardless of sediment age, the organic matter concentration at the surface is not very high. Okay? So these are ponds that have been operated continuously for up to 50 years, and yet we see the organic matter concentration is about 3%. It doesn't change very much. Okay? So a lot of the organic matter that's added to the pond is decomposed. All right? So what we also see, so a young pond, we have this high concentration at the surface, and then it gets down to very low levels, at, in this case, a depth of 10 centimeters. This is the pond that's 23 years old, and it comes down to about 25 centimeters, and then it gets to a low level. In the older pond, it comes down to 45 centimeters before it goes down. So you can see that the organic matter over time gets mixed to deeper and deeper layers, all right? But we don't have big accumulation rates. There's sort of an equilibrium that's established over time. And over here, so this is sort of a categorization of soils, and organic soils might be what you'd find in a mangrove, okay? Real kind of, you'd see the pieces of organic matter in there, real peaty kind of soil. And that's an organic matter concentration of 15%, all right? So shrimp pond soils never get to that level. Usually this is normal, 3, 4%, maybe 5%. So the accumulation rates are really modest over long periods of time. Okay, so you know, these are kind of the ranges that we sort of want to keep in shrimp ponds if we can. You know, and then we have this set of factors that control the decomposition of organic matter. Obviously, temperature controls the kinetics of a lot of reactions and a lot of metabolism by bacteria. pH, neutral conditions, DO, more is better. And then really the ratio of carbon to nitrogen, and I'll return to that. All those kind of control decomposition of organic matter. So what I've got here is a graphic that shows the decomposition rates of different soils. Each of these lines is a soil. And on the bottom, what I've got is the soil moisture content. So on the left side is dry, and on the right side is wet, okay? And in the middle is something moist. It's something intermediate. And on the y-axis, what I'm showing you is the decomposition rate or the metabolic rate of the bacteria that are living in the soil. And what you can see is that under intermediate conditions of soil moisture, you get very high rates of decomposition. Again, each line is a different soil, but the trends are the same. You know, a condition of between 10 and 20% moisture, you get good bacteria activity. And that's because when it's too wet, you can't get oxygen in the soil for the bacteria to work. And when it's too dry, the bacteria need a little water to work, all right? So here in this intermediate condition, you have kind of the best. It's Goldilocks for those of you who know the nursery rhyme. Okay, so when you're drying a soil in between the crops, you get that best activity when you have a little bit of water in there, a little bit of moisture in the soil. Okay, so in terms of organic matter dynamics, the important points are nearly all of the organic matter that you're adding to the pond, both in terms of the feed and the waste that's produced from that feeding, as well as the algae that's being produced from the nutrients from the waste from the feeding, are decomposed, okay? So really, the kinds of organic matter that you're adding to the pond are in a form that bacteria can use easily. They can easily decompose that organic matter. And so you don't see much accumulation, even though you're adding tremendous amounts of organic matter to the pond. Now, a small part, and I showed you that graphic in the budget, a small part, a relatively small part, will accumulate during the production cycle. But in between cycles, if you dry the pond and you decompose that organic matter, you can restore your equilibrium. You can kind of get back to the condition you had before the crop started. Okay, so let's get into the bioremediation topic now. And I want to start with talking about a couple words, okay? One of those words is probiotics, and the other is bioremediators. Now, a lot of people use those words interchangeably, but I want to be a little bit precise about how I use this word. For me, a probiotic is something you add to the feed. The shrimp consumes the feed, there are bacteria there, and it helps to improve the intestinal health of the animal, okay? And it might produce some enzymes and, you know, do other beneficial things inside the animal. A bioremediator is something you add to the pond water or the pond soil to help improve conditions there. It might be the same bacteria, okay, but the work that it's doing is somewhat different. And in this presentation, I'll probably use the word probiotics, but really, bioremediators are something different because of what they do, all right? Yeah, so I just wanted to make that point. Now, if you go out into the marketplace and you look at the products that are out there, many, many different products. And typically, you're going to see these products have a number of different components. And I've sort of listed these there. You have bacteria that produce lactic acid, the lactobacilli. Now, those are really true probiotics. They really can help improve conditions in the intestine. And then you have a whole group of bacteria that don't produce lactic acid, and the bacilli are the big ones there. You have yeast. Saccharomyces is kind of the big one. There are other yeast species there. You have photosynthetic bacteria like these rotobacters, and I'll talk about rotobacters in a second. Then you have nitrifying bacteria, and then aerobic denitrifying bacteria. So those are typically what you'd see in these commercial products. So what I want to do is to introduce you to some of these species and just give you a little overview of them. These are your players in the play, if you will, and probably the most common probiotic or bioremediator that's used in aquaculture are bacillus. Now, there's a reason why. And the main reason is that they produce spores, okay? Spores are very resistant to drying and to decomposition, acid treatment, and so forth. And you see these white dots in here? These are spores. And for anybody who's worked with Artemia, you know, what do? You buy a can of Artemia cysts. And it's similar with what you're doing with bacillus. You're buying a powder, you're buying spores, and you activate the spores and you let them go to work. Now, if you look at the bacteria that are inside a shrimp pond, you know, there are many, many different species. And that was sort of the subject of my talk when I was here in September. But, you know, the numbers of those bacteria that we can actually grow is very small, 1 or 2%. And bacillus is one of those bacteria that we can actually grow in culture. We can plate it out, we can replicate it. So that's really why we use it. Now, it's actually a workhorse. It's a really good bacteria. It does a lot of different things. It has a lot of different capacities. as a true probiotic, it does stimulate the immune system and improves growth performance really by producing enzymes. These are little enzyme factories, okay? And as the feed's moving through, if it's top-coated with bacillus and the spores are activated, it's producing enzymes and it can help improve digestibility. Because what? The transit time of feed in that gut is usually less than an hour, right? So that can really help. And then it can also reduce soil organic matter. So it's a bioremediator in this case. So you can see bacillus functions both as a probiotic and as a bioremediator. All right, I mentioned that the capacities of these bacilli, this group, varies. So I've listed a number of different capacities that these bacillus bacteria have. And those capacities vary according to species and according to strain. And I'm giving you an example here. So here are a number of strains of Bacillus subtilis, and then we've got a number of other Bacillus species here. And these bars are production of different enzymes, protease, amylase, and cellulase. Now, I mentioned that you grow a lot of algae, 3 times as much algae as feed that are added to the pond. And so I would like a Bacillus strain that has high cellulase enzyme activity because cellulase degrades plant organic matter. So you have algae, you have the plant organic matter that's in the feed ingredients. You want to break that down. So I'm looking for good cellulase activity. So this is the green bar. The one with the highest green bar that indicates the activity is this particular strain. Now I know when you go to the market and you're buying Bacillus products and you don't know what the activity is. But I just want to make the point that the activity, all these different kinds of activity varies. And it would be nice to know. It would be nice if the manufacturer had product literature that showed you what the activity is. But somebody did the research to show that. And I just want you to have an appreciation that not all these bacteria are the same. Not all of them have the same activity, okay? So that's an important point. All right, one of the other groups of bacteria that I want to talk to you about is Rhodobacter. This is a really interesting bacteria, and mainly because it has this diversified metabolism. So it can grow aerobically, it can grow anaerobically, it can use solar energy, it's photosynthetic, but it can use chemical energy, it can use an organic source of carbon, or it can use an inorganic source of carbon. So it's very diverse. Depending on what conditions it finds itself in, it can use a number of different substances that are in the pond. It's good for degrading soil organic matter, and it has a variable capacity to denitrify nitrate. The other interesting thing about Rhodobacters, if you look at the intestines of healthy shrimp versus diseased shrimp, you often find Rhodobacters as part of the core microbiota of healthy shrimp. Okay, it's common in healthy shrimp. Now, one of the reasons why it's not commonly used is that it's not a spore former like the bacillus are. And so you have to use a liquid product. All right, you're kind of stuck. Now you can isolate your own Rhodobacter, you can develop your own protocols for replicating it and growing it, but it's a good one, and I recommend it. One of the other things that producers can do with these bioremediators is fermentation. And basically what you're doing is combining a prebiotic, which is basically a fancy name for organic matter, and you can use molasses, you can use rice bran, and you combine it with bacillus and water and some alkalinity, some liming agents to maintain pH, and you do a fermentation for 24 hours, and then you can apply it to the pond. And it can serve as a bioremediator. It can help to digest the organic matter that's at the pond bottom. Some farmers that I've worked with in Ecuador are doing fermented soybean meal, and it's a 2-day fermentation. There's a liquid phase and a solid phase, and then they apply it to the ponds to help flush the gut and it helps get rid of Vibrio. It's a good treatment for EMS. So that's another option as well, is to do some kind of fermentation. Now, when you buy these products, you can buy it in different forms, all right? Liquid is one way. You know, the issue with buying a liquid product is that you're mostly buying water. So if the transportation costs might be an issue, handling might be an issue. But for some species of bacteria, that's basically what you're limited to. You have to use a liquid form. Nitrifying bacteria, for example. There's no dry product for nitrifiers. Rotobacter, the one I just mentioned, must be liquid, okay? Powders are real common. Again, these are these spores that you buy from Bacillus or Lactobacillus. And you can do things like mix fertilizer in there and other product forms before you use them. There are some forms, they would come in these biodegradable bags. It's basically plastic made with starch. And you put it in there and the starch dissolves and they're exposed to water and the spores germinate and go to work. I really like these tablets or pellets. They come in different sizes. They're like pills almost. And the reason I like them is that, you know, most of the bioremediation we're interested in is related to organic matter accumulation on the pond bottom. So if you have a hot spot with organic matter and you can put those bioremediators right on top of it, and you don't have to worry about activation. They're going to activate by themselves and go to work right where you need them to work, okay? So it's a form that I really like. Now, a lot of the farmers I work with in Latin America use this tool. It's called a triangle. And it has basically a metal frame. You can see the metal frame right here that's triangle shaped. And then behind the triangle, they add a net. And they attach a rope, and they throw the triangle out into the pond. And it goes down to the pond bottom, and they pull it back in. And then you can look at the mud that you bring back in, and you might see some molted shrimp or some diseased shrimp. And it's sort of a way to check what the conditions are on the pond bottom. And based on the conditions that you have, you can develop your own protocols for bioremediation. So if you've got soil that you have good oxygen conditions and the soil comes back looking like this, it's got a nice smell. You know, I encourage people to smell their soil. You know, use all your senses. And you can decide, you know, what you want to use. I mean, it's good conditions, so things are fine. If you've got low oxygen in the pond, the soil is black like this, and you've got some shrimp with spots, melanization, then you probably want to add some bacillus as a bioremediator, and then maybe some lactobacillus to the feed to help with the internal conditions. If you have very low oxygen and black soil and a bad smell of rotten eggs and some dead shrimp, then you can use this bacillus and lactobacillus, and then you can add Paracoccus. And I'll come back to Paracoccus at the end here, but the point is that you can use this triangle if you have a soil-based system. Even with liners, probably, you could use this triangle to help guide your decisions about bioremediation. Okay, so here's just an example. I'm not saying this is the program that you should use, but this is an example of programs that are used by farmers in Ecuador. And again, the intensity is a lot less, so this may be adjusted. So based on the concentration of organic matter in the soil, in this case, they're adding a certain quantity of a nitrate source, okay? Why am I doing that? I mentioned earlier that one of the factors that affects the decomposition rate of organic matter is the ratio of carbon to nitrogen. And basically, the bacteria are taking up carbon and nitrogen in more or less a fixed ratio. Now, the organic matter that's in a pond has got plenty of carbon and often is missing a little bit of nitrogen. So if you add some nitrogen, you can actually stimulate decomposition. The nitrate actually has some other beneficial attributes that related to the chemistry of the sediment that I won't get into. But the point is that the form that you add should be a nitrate form, not urea, not an ammonia form, okay? and that will be beneficial. And then here's just, again, an example protocol of using these pills depending on your production intensity and how many per hectare that you would apply. You would probably want to develop your own protocols, but this is just an example of one. Okay, so I always recommend a dry out between crops. Now, a lot of farmers really want to minimize the time that the pond is down because they're not making money when there's no water in it, when there's no shrimp being farmed. So farmers are they really want to turn that pond over between the harvest and the next cycle. And so here's a couple examples of some protocols that you might want to use. If you have the time, dry the pond out completely. And you may want to add some bacillus bacteria as a bioremediator. And if you've got a lot of sediment accumulation, you might have to mechanically remove it. Now, a lot of farmers really want to turn that crop over quickly or turn the pond over quickly, and so they would use, again, I would recommend a nitrate form rather than urea as a nitrogen source, and then you could bioremediate and proceed with your dry out or your turnover quickly. Because shrimp crops tend to be fairly short, let's just say 90 days, that, it's not necessary, I think, to dry out completely every cycle. But I would say every year and a half, probably want to do, kind of a normal dry out. And then in between, say, 2 or 3 crops, you could do just a quick turnover, all right? But you will have a modest accumulation of organic matter through the crop cycle, especially if you don't have enough oxygen at the pond bottom. All right, a lot of farmers now are using these automatic feeders, all right? And especially those with the timers, if you don't tune those timers properly, the tendency is for the shrimp to be overfed. And when the shrimp are overfed, this is what you see on the pond bottom. You see accumulation of organic matter. So in ponds where you have automatic feeders, you should focus your bioremediation efforts on those zones because that's where the feed's going. So put the pills there, put your nutrients, put your probiotics in those zones during and between the crop cycles. All right, a little bit about the water column. Some of the farmers I work with, when they're bringing water in from outside, it has a lot of organic matter in it. So they've developed protocols to use liming agents like calcium hydroxide and calcium oxide basically as oxidants. Okay, it basically kills the organic matter and it helps it to settle and it reduces the amount that's there. You can use hydrogen peroxide for the same thing. You can use potassium permanganate. There are many other chemicals that can be used. And so it really kind of depends on the conditions of your water. This is not, I'm not talking about sterilization. I'm not talking about chlorination here, but I'm talking about really reducing organic matter. And just as a side note, I think there's way too much sterilization of water here in Asia. If you're going to sterilize water, make sure you're adding life back to it before you put it to the shrimp. Yeah, so and sometimes if you've got a lot of suspended particles, the water looks very muddy, you can add alum, aluminum sulfate, to help precipitate that turbidity, that mineral turbidity. Okay, now sometimes during the crop cycle, you might see a peak in ammonia, okay? And there's a way to manage that peak in ammonia that you might see by adding carbon. And by doing that, you're encouraging the growth of heterotrophic bacteria. And that response is very rapid. So if you add molasses to a pond or sugar, within 6 hours, you're going to see the ammonia concentration go down. It's very rapid. You have to be prepared because you're basically growing a lot of bacteria all of a sudden. And that's going to create an oxygen demand, and you're going to have a lot of organic matter on your hands to contend with. If you have a central drain, get it out of there, okay? Because those bacteria cells are basically temporary packages for that ammonia. If you let that bacteria die and decompose, it's just going to release that ammonia back to the water. So you want to capture that, package it into bacteria cells, and get it out of the system. That should be the thought process on that. And I've given you a couple examples of how to manage. You know, if you're going to sort of encourage, you know, like this is from biofloc systems, and you want to encourage some kind of level of bacteria growth in your systems, you can add some molasses in relation to the feed that you're adding. You know, I have little hesitation about recommending molasses addition because it does tend to encourage Vibrio growth. And, you know, for various reasons, that's not necessarily desirable. So, you know, this should be done with caution. But if in an emergency situation, which is where you get these peaks of ammonia, if you're up at 4 or 5, 6 milligrams per liter and you want to knock it down, you know, for every milligram per liter that you want to reduce that ammonia, you can add this much molasses, all right? So I've kind of gone through the calculations there of the carbon to nitrogen ratio that you need to keep that ammonia low. Yeah, so like I say, 6 hours. This is a pretty rapid response. This is a good bioremediation approach. It's just add inorganic carbon. All right, let me, at the end here, talk about hydrogen sulfide. You know, this is also a serious issue, both in ponds with soil and ponds with plastic liners. And so it's really a byproduct of the decomposition of organic matter and the reduction of sulfate. So seawater has abundant sulfate in it, which is an oxidized form of sulfur. And down deep in the sediment, under these anoxic anaerobic conditions, sulfate is chemically reduced to sulfide by bacteria that live down there. And if you don't have that thin oxidized sediment surface layer that I was talking about, that sulfide can diffuse out of the sediment into the overlying water. If you have that little skin, that little barrier, it can't escape, okay? So that's why it's important to keep that oxidized sediment surface layer, to keep that sulfide from coming out of the sediment. And you'll know, it's common, you smell that rotten egg smell, okay? It's extremely toxic, potent toxicant to shrimp. And of course, shrimp are a lot of times moving around on the pond bottom. They're looking for feed, they're moving around in the sediment, and so that disturbance can expose them to hydrogen sulfide. So I want to talk a little bit about black gills. I don't know if any of you have seen this issue when the gills of the shrimp get a black color. It also contributes to white feces, although I don't want to confuse you with EHP issues and hydrogen sulfide. It's also a real problem with shrimp that have molted. So when shrimp molt, their metabolic rate is really high, okay? It's much higher than post-molt shrimp. And as such, this effect of hydrogen sulfide is magnified. And it's also toxic to nitrifiers, which are desirable bacteria that you want. Okay, so here's a normal shrimp gill right here, and here's a shrimp with black gills. Now, this is often called black gill disease. It's not a disease. There's no microbial agents involved other than the bacteria that are reducing the sulfate to sulfide. But it's not a pathogenic bacteria like the Vibrios that cause EMS. And this is basically what's happening. So you have hydrogen sulfide that's released from the sediments. If you don't have that barrier, hydrogen sulfide comes up into the water, and that hydrogen sulfide irritates the gills. Okay, that's part of its toxicity. And in response, the shrimp produce melanin granules. Now, melanization is a very typical immune response of shrimp to any outside invader. It might be a bacteria. In this case, it's a toxicant. And so the gills produce this melanin granules, and they accumulate. So here's a normal gill, and here is a black gill. And these dots in here are granules of melanin. And what those granules of melanin do when they accumulate, they interfere with the ability of the shrimp to obtain oxygen from the water. all right? So you might have good oxygen concentration in the water, but the shrimp is like dying for lack of oxygen. So they actually experience what's called hypoxia. And so shrimp could die or basically be toxic, even though, hey, my DO looks great. But no, they can't get that oxygen because of all these granules. Now, when the shrimp molt, if conditions are good again, those granules go away, all right? So it's not, again, it's not a disease. It's more like a syndrome, really, of exposure. All right, so I mentioned this before, one of the bioremediators that you can use if you have a black gill problem is this Paracoccus, all right? And it's a commercial product. I'm not promoting particular, I'm not making commercials here, but this is a product produced by Novozymes, and it's effective. So if you look here at this green line, these are a couple different doses that you add. These are the controls where there's no sulfide in here, and you can see very quickly, within a few days, the hydrogen sulfide concentration goes down, all right? So it does address that. And if you add it through the culture cycle, you get greater body weight, growth, better survival, lower feed conversion, and higher yields. I mean, if you don't have a hydrogen sulfide problem, you don't need to add this stuff. But if you have a pond that historically or chronically has hydrogen sulfide issues, or you have black gill disease, I shouldn't have even used that word. If you have black gill, then you can consider using this Paracoccus. And it's also a denitrifier, which helps to get nitrogen out of the pond too. So it has that other benefit. All right, so you need to have a certain set of conditions to do bioremediation. You have to select the right organism for the job. And so you have to know what you're trying to bioremediate. Normally these commercial products, it's a mixture, okay? They have a certain number of strains, so you have to just kind of look and see what's there. And so a lot of those are pretty effective. On the packaging, they'll normally tell you what is the effective dose. So you want to look at this number here, this 10 to the 8th, okay? So it's an indicator of the concentration of bacteria. You want a concentrated product. You don't want to add a dilute product. So look for something 10 to the 8th, 10 to the 9th, 10 to the 10th. Those are all good. And most of them are these freeze-dried products and these spores that I talk about, and you're basically activating the spores. Now, I do recommend following the protocols that are suggested by the manufacturer. I visited many farmers. They think they have something better. They think they have better protocols for activation of these bacteria, but just follow the directions. Make it simple on yourself. And then when you're storing these products, keep it like in a room like this, air-conditioned, dark, cool, dry, just if you're not going to use it right away, okay? Good storage is important. Now, sometimes these bioremediation products don't work. And you might say, okay, why did I buy this product and it's not doing what it says it's doing? Well, there may be some reasons why it doesn't work. Normally, ponds contain huge numbers of bacteria. And often it's not a number, or density, it's not a particular species that's missing, it's something more fundamental. You're not providing enough oxygen for those bacteria to work. So if you don't have good oxygen conditions, you can add all the probiotics or bacteria that you want, and you will not achieve that positive effect. So, consider the fundamental characteristics or criteria that are needed for those bacteria to function. Sometimes, you have these unscrupulous dealers and they just putting a bunch of powder in there and you really don't know. So use a reputable brand of products. And just as a sidelight, I was reading a story some months ago about some research was done in India on what are called informal probiotics. And what they found was that when they looked at those bacteria, they found genes for antimicrobial resistance in those bacteria. Now that's a problem. okay? Antimicrobial resistance in aquaculture is a serious issue. Don't be part of the problem by using informal products that are just going to replicate those genes in the environment, all right? Use reputable products. And another reason why these programs fail is that, you know, every pond is different, and so you have to adjust your program, get skilled in understanding how it works and what is the best application protocol. Adjust the recommendations based on your conditions. Okay, just to summarize here, and I want to go back to the definitions, probiotics and bioremediators. Probiotics are improving intestinal health. You add it to feed. Bioremediators, you add to water or soil to improve conditions there directly. You can also use fermented products. Good choice. You know, I know farmers in Asia are using a lot of fermented rice bran. And just let me mention that if you're going to use rice bran and as a fermented product and apply it, be very careful. One of the critical criteria is using rice bran that has been screened. That rice bran should be 200 microns or less. That's a very small particle. And the reason is that those small particles will stay in suspension. If you use larger particles than that, all you're going to do is add a lot of organic matter to the pond bottom and you're going to create a mess, okay? So if you want to use fermented rice bran as a bioremediator, screen it first and use it carefully. Get skilled with applying that. So yeah, you can add various types of bacteria. I've gone through a few examples of some of the species that are out there that you can use. And I said, you know, this is true definitely in Ecuador, and I know in Asia there's also a lot of automatic feeding going. So there tends to be concentrations of organic matter in ponds, and you know, you kind of get a feel for where those are, and focus your bioremediation efforts on those areas where you have hot spots of organic matter accumulation. If you can get it out of the pond with a central drain, that's great. It kind of minimizes the need for organic matter. Yeah, so on this last point, I didn't mention this previously, that you know, what I've seen with bioremediation, you know, if you have an extensive pond and you have an automatic feeder, yeah, you can focus your efforts there where the feeders are. You know, sometimes these programs don't work in extensive ponds, mainly because you're already operating within the carrying capacity of those ponds. Now, with intensive ponds, you're always sort of pushing the limits. And in many cases, those systems will not function without additions of bioremediators. It's sort of part of the technology package. Okay, so as production intensity increases, the importance of bioremediation also increases. So I'll leave you with that point. And once again, thank you for your kind attention today.